Okay, I think this is going to be the last video that we'll have in this class. So anyway, right now we're going to get into regression analysis. This is a little bit more complicated than the content that was related to correlation coefficients, coefficients of determination, and so forth. And actually what you'll find is as we go through this discussion of regression, we'll also come back to a couple of those concepts. So anyway, some of you may have done regression analysis before, perhaps didn't even know it if you looked at the straight line equation. I know sometimes that may be studied in the algebra class. But anyway, I went ahead and prepared quite a few notes here. And I did that to assist you so that in the event you need to go back and hit pause and get some of this down, whatever, then that sounds good. But anyway, what we're going to do in the case of regression analysis, and let me start off by saying that all that we're going to do is look at simple regression. And in the case of simple regression, we have one independent variable and one dependent variable. Okay, later on when you get into data analytics 2, you'll be studying multiple regression, in which case you'll still have the one dependent variable, but you'll have two or more independent variables. And what you'll find is that in terms of predictive capabilities, that multiple regression is superior to simple regression. But again, we're at the end of the course. I know we're moving relatively quickly here, so I sent a message to everybody to this effect, but I just don't think we're going to be able to really cover multiple regression to the point that it'll be understandable to you guys and fair to everybody. So anyway, okay, let's get going here. Regression uses a straight line equation in order to predict the value of the dependent variable based on knowledge of the independent variable. And this is the overarching purpose of regression. Again, it is to be able to predict the value of the dependent variable based on our knowledge of the independent variable. This is our straight line equation. In the textbook, you'll find they use y caret to indicate the estimated value of y. I tend to use y prime. It's just my preference. You can use either one. But what we're saying here is that the predicted value of y equals a plus bx. Okay, where this is y prime, predicted value of y, which will be our dependent variable. Okay, and remember the independent variable is manipulated to determine the effect upon the dependent variable. The a, this will be the intercept, and it is the value of predicted y whenever x equals 0. Okay, so we have a situation like this, x, y. This would be our intercept right here. It's the predicted value of y whenever x is back here at 0. Okay, the slope is the rise over the run. It is the average change in predicted y for every 1 unit change in x. Do note that the slope can be either positive or negative. Okay, so if you're doing one of these and you come up with a negative slope, don't be alarmed. Okay, again, it's just a change in predicted y for every 1 unit change in x. Sometimes as we change, for example, as we increase x, sometimes predicted y goes up, sometimes it will go down. Again, that'll be given the nature of the two variables. And x is the value of the independent variable. We will also refer to that as our predictor variable, okay? So again, we use the predictor value as the independent variable in order to predict the value of the dependent variable, okay? And note here that b, the slope, is also referred to as our regression coefficient, okay? And on page 449, take a close look at this least squares principle. Essentially, what it's telling you is that, switch this over here, they actually started on 448, it runs to 450. But here we have the least squares principle, a mathematical procedure that uses the data to position a line with the objective of minimizing the sum of the squares of the vertical distances between the actual y values and the predicted values of y. Okay, so you see this right here. This would be a straight line that really best cuts through the data. This is also referred to, wait a minute, let me get this, sorry about that, as the line of best fit, okay? So again, what we're going to have is we're going to have various data points, okay? And let's say we have data points that are kind of like this, okay? And what we would do in the case, this would be our x and our y, we want to create an imaginary line that cuts through this data in the best way that minimizes the squared deviations between each data point and that imaginary line. Some will be above the line, some will be below. But what we want to do is to find this line of best fit that best cuts to our data points, okay? And this will be our regression line, and its angle will determine the slope. Okay. So there are some equations in the textbook for the slope and for the intercept. And those are over here on page 450. Okay, you'll see here the general equation, predicted y equals a plus bx. This is our regression equation. Down here, you get the slope and the intercept, okay? And the slope, you can take that by calculating the correlation coefficient, which we've already done, times the standard deviation of y over the standard deviation of x, okay? It's perfectly fine to do it that way. Okay, that's not a problem at all. And then to calculate the intercept, we're going to take the mean of y minus the slope times the mean of x. So you see that we have to calculate the slope before we can calculate the intercept. Okay, but what I want to do is I want to give you an alternative equation. Okay, and this is going to be our alternative equation. Okay, we're going to take n times the sum of xy minus the sum of x times the sum of y over n times the sum of x squared minus the sum of x squared. And I know this may look a little more cumbersome than the other equation, but if you do the other one, particularly by hand, then you're going to have to calculate the standard deviation for both x and y, and that can take a while. So what you'll find is that in using this equation, you're probably going to find it a little bit easier. And what I've done is I went ahead and included the data that I used in the previous video where we had the 6 data points. Hang on a second, let me grab those. Okay, recall that we were looking at the relationship between the number of showings and the number of homes sold. Okay, so all I'm doing is taking the data that we already have here, and I'm going to plug them into this equation. So again, we had 6 data points, and the sum of x times y was 7857. So we're going to take 6 times 7857 minus the sum of x, which was 376, times the sum of y, 111, over the same 6 over the sum of x squared. The sum of x squared was 27,000 minus the sum of x, and then take the sum of x and square that value, so that would be 376 squared. And if we bring that on down here, I went ahead and worked this out. There we go. And you'll see that we come up with a slope of 0.2621218. And I know I carried that out there pretty far, but as we'll see in a little bit, there's a reason why I did that. And again, this is an alternative. We've already calculated the sum of x times y. We got the sum of x, we got the sum of y, we got the sum of x squared. So it's real easy just to pull those from the work we've already done and calculate the slope. Now this slope of 0.262, note that it is positive. And now that we're saying is this, within the context of this problem, this means for every additional showing, the number of houses sold increases by 0.262, so a little over 1/4. Okay, so again, that's the slope. It's the change in predicted y for every 1 unit change in predicted x. Okay, so anyway, so if somebody had 10 showings, we would expect the number of homes sold to increase by 2.62. Okay, so the intercept, and this is the same equation that we have in the textbook. This is the intercept. It is the mean of y times the slope times the mean of x. And the mean of y, we got the sum of y, which was 111. There were 6 data points, minus the slope, which we just calculated, times the sum of x. Remember the mean of x, rather, that was the 376 over 6. And if you calculate that out, you should get 18.5 minus 16.42629947, and we get an intercept of 2.0737. So if we drew that graphically, it would look something like this. This would be our intercept, which would be the 2.0737, and this would be our slope. Okay, that's all that we're doing. And again, we're using this for predictive capabilities with the goal of saying, okay, Sam, you sold 71, you showed 71 homes. This is your predicted level of sales. Okay, you may use that in your recruitment. Okay, you say, hey, if you work this hard, you're going to make this amount of money or sell this many houses and accordingly make this amount of money. So anyway, that's why we're doing this. Okay, so this is a bit of a repeat of what we got there. In the context of this problem, the intercept value of 2.0737 means that if there are no showings, the predicted number of homes sold is 2.0737. And you're probably thinking, how can you have no showings and still sell a house? Well, this points to one failing of regression. Okay, it tends to work only within a relevant range, and there will be times when your regression equation will give you illogical conclusions. Okay, that's just part of regression. Okay, I've done it before where we were looking at predicting electricity usage based upon the number of rooms in a house. And you'd find out that, well, if we have 0 rooms, we're using X amount of electricity, which would make no sense because there's no rooms, we don't have a house. But anyway, that's just the nature of it. So again, if we graphically depicted this, I did this earlier, this is going to look a little bit better. This is our regression equation, predicted y equals the intercept plus the slope times the value of the independent variable, that's x. So go ahead and put that, and this is graphically depicted. So if we have an agent who shows 50 homes per year, it is expected that he or she will sell how many homes? Okay, let's go ahead and figure that out. I forgot to put this in here, 15.18, and we got that by simply taking the intercept 2.0737 plus 0.2621208, and here the 50 homes, we plug this in as our independent variable. So we get 2.0737 plus 50 times 0.2621218, which is 13.10609. And we end up getting 15.18 homes. Okay. So again, that's regression. We've covered how to calculate the intercept and the slope. We understand why we're engaging in regression. Now, one thing that you want to look at when you're doing your regression is you want to make sure to test for the significance of the slope. Okay, and now in this particular case, our slope was 0.2621218. Okay, that was our calculated slope. Okay, so if our slope is significantly different from 0, then we know that it increases the predictive capability of the regression equation. But you have to test for this. Okay, and the way we're going to do this is the notation for a population slope. And so our null hypothesis is going to be that the slope is equal to 0. The alternative, excuse me, equation being that our slope is not equal to 0. Okay, so again, the B denotes the population slope, and we're going to have to calculate T. This is in the textbook, okay? And the equation here, before we do the equation, we're going to use an alpha value of 0.05. That's been pretty consistent throughout this course. And also, too, our degrees of freedom will be equal to the number of data points minus 2. So in this particular case, we had 6 data points. 6 minus 2 equals 4. So we know that we're going to have 4 degrees of freedom when we go to our T distribution. Okay, so the T is going to be equal to our slope minus 0, so it's going to be the slope over the standard error of the slope estimate. Okay, now this is where it gets a little tough. Okay, again, that's going to be this notation. This is the standard error of the slope. Okay, so let's go ahead and move this on out and talk a little bit about what the standard error of the slope is. But before we do that, what I'm going to do, let's go ahead and show you what happens when we do this in Megastat. Okay, so I'm going to go ahead and before we get into the standard error of the slope, because it's part of our Megastat printout, let's go ahead and do that. So let me share the screen. Okay, and here we have our values. Okay, I've already plugged them in. These were the independent variables, the number of showings. Here's our Independent variable number of showings, dependent variable would be the number of homes sold. I've got that in. We're going to go to Megastat. We're going to go to correlation regression. This time we're going to go to a regression analysis. And it's going to ask for the independent variables. Let's highlight those. For the dependent variables, highlight those. I want to go ahead and put in this 50 as our, you don't have to do this, but I want to go ahead and put in, type in a predictor value. Since we've already looked at 50, let's go ahead and prove that. So we're going to put in a predictor value of 50. And all I'm going to do here is I'm going to click on this standard coefficient or the betas. That's pretty much all we're going to need to have here. I would like to get into some of this. This is pretty sophisticated, definitely beyond the scope of a Data Analytics 1 course, but let's go ahead and hit OK. And see what happened there. There we go. I'm not sure what happened there earlier. Okay. This proves what we came up. Remember when we calculated this earlier, we came up with an intercept of 2.0737. We've already done that. So this is the value of the intercept, and this is value of the slope. So when you see this x1, we only have, if you have multiple regression, you have x1, x2, x3, x4 if you had 4 independent variables. Here we only have 1 independent variable, so it's going to be the x1, and this is the slope. So look right beside the x1, you'll see the coefficient. That is your slope, and there's the slope 0.2621. We've already calculated that. Okay, so I want to stop that right now. We may come back to this in a second, but do note here, we've got this standard error of 0.0657. Actually, what I've got, I think I've got a printout of this, so we may go ahead and use that when we bounce out of here. So let's stop the sharing and go back. Okay, so in terms of testing the significance of the slope, if our slope is significantly different from 0, then we know that it increases the predictive capability of our regression equation. So if it's not different from 0, then really that beta coefficient is not helping us at all. So we're going to test for that, okay? So again, we've already gone over the known alternative hypotheses. We said that t equals the slope minus the standard error of the slope. We said we're going to have an alpha 0.05 degrees of freedom will be n minus 2. Let's talk real quickly about what the standard error is. The standard error is a measure of the variability or dispersion of the observed data points around the regression line. It is calculated as the standard deviation of the residuals, which are the differences between the observed values of the dependent variable and the predicted values of the dependent variable based on the regression equation. Okay, so we know that when we have a regression model that very, very rarely would you have a situation where the predictive capability was perfect. In other words, if we simply plugged in the value of the independent variable, we would automatically know exactly what the dependent variable was. Okay, odds are that's never going to happen. So again, we're always going to have some error between what the predicted values are going to be given a given independent variable and what they actually turn out to be. Okay, so if you look at this, you'll see that we had, we're going to do that. And when we went back into Megastat, we had this 0.0657 as our standard error. So let's go back here and let me show that again. Okay, remember we had this standard error 0.0657. So we're going to take that in and plug it in our equation. Okay, and we come up with 3.9893. Okay, so that's our calculated t statistic. And if you go to your t charts, hang on just a second. I try to never stray too far from t. Okay, here's our t distribution. Again, we've got two tails, 0.054 degrees of freedom. 6 data points minus 2, we see 2.776. Our calculated t was 3.9893. So we're going to reject the null. And so we're going to say that the slope of the regression equation does indeed differ significantly from 0. Thus, it does increase the predictive capacity of our regression equation. Let's get this up there. And then we'll leave that there for a second in case you're taking notes. Again, in this particular case, the regression equation or slope, the regression equation the beta coefficient is significantly different from 0, so it does have some predictive capability. Okay, this is another way to calculate the standard error of the estimate. Okay, I was going to do that by hand, but I think we're just going to pass on that. We've already used Megastat, we've calculated. If you're really interested in this, this will be the equation from the textbook, so feel free to go and practice some of these on your own. I'm sure that probably the vast majority of you will jump right on that. Okay, the last thing that we're going to talk about is an ANOVA table. And if you go back and look at our ANOVA table, we had one that was provided here. And hang on just one more second. Let me see if I can get a copy of this regression output. Here we go. This is our regression equation. Okay, I printed out a copy of this. And you'll see, remember, this was our intercept. This was our slope. This is our beta coefficient. This was the standard error. But also, lo and behold, we've got an ANOVA table up here. Okay, and you may be thinking, hey, we did ANOVA in another model. Okay, ANOVA and the F distribution by its very nature, it deals with variation of data. Okay, so ANOVA can also be used in the case of regression. So anyway, so earlier we talked about coefficients of determination. And if you recall that, we said that our R squared is going to be assuming that there is a causal relationship. Okay, it tells you how much of the variability in the dependent variable can be explained by the variation in the independent variable. And again, all that we did is we took our correlation coefficient and we squared it. Okay, so in the present example, if you remember when we did this in the earlier video, we came up with an R square of 0.7992. So if you look at how we do this on using our ANOVA table, we can simply take the sum of squares regression and divide it by the sum of squares total. So there we're going to take, let's see if we can get them both in here, this 236.1717 over 295.5, and we'll come up with that same R squared. Okay, so again, if all that you have is an ANOVA table from a regression output, you don't have to run the correlation to calculate the R squared. Okay, because it's going to be given. Again, we're going to get that by taking the sum of squares regression and divide it by the sum of squares total. Okay, also too, what that means, if we've got that, we've got the 0.7992, if we go ahead and take the square root of that, we get 0.89397, and that's going to be our correlation coefficient. Okay, so again, if we take the square root here, we're going to get the correlation coefficient. So again, the R squared, you can go from R to R squared or from R squared back to R. Instead of using the exponent, you take the square root. Okay, and there is another way. Okay, we've already come up with that correlation coefficient. What you can also do is you can take 1 minus your sum of squares error or residual over the sum of squares total. So going back at looking at this, our sum of squares residual was 59.3283. You see that? Sum of squares total, 295.5. We're going to take 1 minus that. You end up getting 1 minus 0.200772589, and boom, you get the same 0.7992. So you can use either of those ways to calculate your ANOVA table. Okay, that ends this video. I encourage you to review it. You may need to review it a second time. I've also got all kinds of information here in the module dealing with linear regression with correlations, coefficients of determination, beta coefficients, standard error of the estimate, and so forth. So hopefully that'll be helpful. This is definitely going to be one of the more rigorous modules that we're going to go over. But again, take your time with it. You're going to have some really good homework problems to do with this. Be sure to watch this video before you attempt any of that, and you should be in good shape. It's been a real pleasure having you guys in class. We're not finished, but this will be the last video. So everybody take care. Do really well for the end of, from now to the end of the course, and good luck in data analytics too. Take care.